material in the book is covered in sections 8.2 and 8.3. 8.2 is the law of sines, 8.3 is the law of cosines. And then we talk in 8.4 about area of triangles, which is at the very end of this, but not super important to me. So I'm going to talk about 8.2 right now, law of sines. I gave you a little bit of an introduction about when you can use the law of sines. It was kind of sloppy and not my best work. But instead of going back and trying to clarify that, let me just tell you what the law of sines is. And show you how to use it. And we can talk about the ambiguous case. The law of sines is written right there. If you have a triangle, right, labeled so that the angles are capital A, B, C. And remember we said there's this sort of standard labeling where opposite side lengths are the lowercase letters. So if you have a triangle labeled in this fashion, whether it's a right triangle or not doesn't matter. You can write the following equation. Little a over sine big A has to equal little b over sine big B has to equal little c over sine big C. And this is actually three equations written on one line, right? I mean, these guys always have to be equal. These guys always have to be equal. And these guys always have to be equal. Okay, so this string of equality is trying to give you three equations. So this is going to help us solve triangles that aren't right triangles, right? Remember, triangles that aren't right triangles are called oblique triangles. So this little formula is going to help us solve oblique triangles. I did a quick example showing you where this comes from. I want to go over it quickly. I don't want you to think this is magic or somebody randomly made this up. It's pretty easy to verify that the law of sines is true. So the way you kind of verify this, the way you come up with this equation, is you take your oblique triangle and you turn it into a right triangle. Okay, so if you look up there, I took a standard labeled triangle and I turned it into a pair of right triangles by dropping what we call an altitude. So what I'm going to do is come up with part of this equation using sort of previous trig knowledge about right triangles. And as soon as I drop this altitude, I can start doing my normal right triangle trig. So for example, I can talk about what sine of A has to equal. And I can also talk about what sine of C has to equal. In this triangle, how could you write sine of A? What is it equal to? So A is this angle. What's the opposite side for A? H, right? If you're focusing on this right triangle, H is the opposite side. And what's the hypotenuse? C. Okay, but now turn your attention to the other side. There's another right triangle over here. So sine of C can be written as what? H over A. Both of these have an H in them. So if you solve this guy for H, what do you get? H equals what?
Sine over C.
Multiply the C up, actually, right? If you multiply C on both sides, H is equal to C times sine A. And what happens over here if you solve for H? A times sine C. But if this is H and this is H, then these have to be equal. So this implies that C sine A has to equal A sine C. This is a more convenient format because it's easier to remember, right? A over sine A is the A's go together. C over sine C, the C's go together. So you can turn this equation back into this format by dividing. Right? If you divide sine C over to the other side, you get your C over sine C. And if you divide the sine A over as well, if you divide both sides by sine A, this will become C over sine C equals A over C.
How do they cancel out? Like the top one we just did.
What?
How does it cancel out right there, like on the top one? Like you said, it equals C over sine.
No, I'm saying this is true. Right? This is true.
And then when you divide it, how does it cancel out so that it equals C over sine C? Doesn't it?
So I'm going to divide both sides by sine C because that's a valid operation. Like if I have an equation 3x equals 5, I can divide both sides by 3, right? So I'm saying I want to isolate A, so divide this out, which is fine as long as you do it to the other side. So I'm just using algebra to solve, using algebra to isolate A. And then I use algebra again here, dividing both sides by sine A, brings the sine A down. So the law of sines is really just what you get from two different right triangles sitting in an oblique triangle. Right? We only did this equation, but you can do the same thing with A and B and C. You would just have to drop different altitudes.
Right.
So like this guy here would give you two right triangles to use for B and C. Okay, well, if you understood any of that, great. If you didn't, that's great, but I can work with it. Solve each triangle. Okay. So I give you information about a triangle. Right? A equals 56 degrees, B equals 25 degrees, and A equals 12. So big A is the angle. Big B is another angle. And little a is a side length. So I'm going to draw a diagram to help me keep track of everything. It won't be to scale because I don't want to waste a lot of time. But let me label my side lengths and my angles that I know and the ones that I don't know, so I can keep track. So here's A, B, C. Remember, opposite side lengths you label with the lowercase letters. And then what I know is A is 56 degrees, B is 25 degrees, and little a is equal to 12. So what I don't know is big C, little b, little c. So we have to solve this triangle. What are we going to solve for first? Big C, oh my god, big C, please, right? Because you know two of the angles, so you can get the third angle by doing 180 minus the other two. So this is the case we talked about a little bit. This is almost the case that we talked about a little bit. Right now I'm given two angles in the excluded side length, so technically I'm given angle, angle, side. This is not one of the four cases that we usually talk about. And the reason that this isn't one of the four cases that we usually talk about is because if you're given two angles, you can always solve for the third angle. Right? So I'm going to actually turn this into angle, side, angle in just a second. So if I solve for C, big C, then I would take 180 minus 25 minus 56. So 99. So now I know big C is 99 degrees. Which means I've changed this into an angle side angle problem, which is one of the cases I can actually solve with the law of sines. If you try to apply the law of sines before you get this angle with just these three pieces of information, it won't work. Because the law of sines says A over sine A equals B over sine B equals C over sine C. If you take out this angle and you just try to put little a is 12 or big A is 56 and big B is 25, you'll be able to get little b, but you won't be able to get any of the c's until you subtract. Okay, because you don't have either piece of this information. So you do have to remember one valid manipulation here is subtracting from 180, right? But that's pretty easy. Most people do that. So we got our easy angle, which turned it into a problem we can now use law of sines on for everything. How do you solve for, or what do you want to solve for next? Well, we don't know little b, we don't know little c. Which one do you want to find?
Little c.
Little c, good choice. If I'm going to solve for little c, now that I know big C, I can compare this ratio. Do you think I should use this equation? Should I compare C over sine C to B over sine B? No, because I don't have enough information here. I'm missing two pieces. So instead, compare to A over sine A. So I will use this portion of the law of sines. I know little a is 12. I know big A is 56. I don't know little c. I know big C is 99. Fill it all in. To solve this for little c, I would multiply up my sine 99. So I'll get 12 sine 99 over sine 56 equals little c. And that's what you put in your calculator. 12 times sine 99 over sine 56.
Does it matter if your ingredients or degrees?
Because we were given information in degrees, you're going to want to be in degrees. And in general, with law of sines, law of cosines problem, degrees is what we use. What do you get? 14.2964. Now, anybody else get that? Mm-hmm. Okay, all right. So the instructions say, round your angle measures to the nearest degree and side lengths to the nearest tenth. It would make me happiest if you did not round until the end. I mean, you can round to 4 decimal places. I don't need you writing out 12 decimal places. But if you start truncating things at the very beginning, if you use that later, it makes your error that much bigger. So when I'm completely done with the problem, I'll round this to the nearest tenth. But until then, I'll keep 4 decimal places. Slightly better. Slightly less error that way. So how am I going to solve for little b now? Right, that's the only thing I don't know. These are my only unknown. What can I set up? Pythagorean theorem? Right, because I know C and I know A, so now I can get B with the Pythagorean theorem? No, why not? It's not a right triangle. So don't ever use the Pythagorean theorem when you're doing law sines, law cosines. Because you don't have a right angle. Instead, set up law sines again. Sine A, oh I'm sorry, A over sine A should be equal to B over sine B. That's this equation right here. I know A, little a, big A, and I know big B, so I can solve for little b. Just plug in what you know. So 12 over sine 56 equals B over sine 25. Multiply it up. A lot of click clack. That's good. Click, click, click. What do we get, team? 6.117234. But there's 2 ones, right? Yeah. So what are my answers? I was given big A, big B, and little a. I found big C, little b, and little c. Big C is 99 degrees. Little c rounded to 1 decimal place because that's what the instructions say. And we're done at this point. And then little b rounded to 1 decimal place. Easy enough? So with law of sines, if you're ever given 2 angles, you can find the third instantly, right? That's just because it's a triangle. And then at that point, you apply your law of sines and you will only ever get 1 answer. There will only ever be 1 answer at every step. Okay? However, if you look at part B there, I have another triangle and I haven't given you 2 angles. I've given you 2 side lengths instead. Look at what happens here. I think little a is 30, little b is 20, big A is 15 degrees. I'm drawing a schematic. Write down what I know. 30, 20, 50. I'm missing this. So I can't subtract anything to get my other angles yet. However, let's start this. So this is the case where I have side-side angle. 2 sides in the excluded angle. look at the law of sines, A over sine A equals B over sine B equals C over sine C. I know little a, big A, and little b. I know this guy's 50, this guy's 30, and this guy's 20. So I can start off right here and solve for big B. So in this case, since I can't subtract to get my angle, I have to use law of sines. So I'll set up 30 over sine 50 equals 20 over sine B. So one quick way to get rid of your denominators, I don't remember this from a long time ago, you can cross multiply. 30 over sine 50 equals 20 over sine B is the same thing as 30 sine B equals 20 sine 50. And then if you divide by 30, you have your sine B isolated. So we're one step closer to getting B. So go ahead and find me a decimal for this guy here. Give a chance. Sine 50 times divided by 30. Should I do it? 0.51067. That's great. That's sine D. Is that what I was looking for?
No.
So what do I have to do with this? Okay, now this is where your life gets a little tricky. All right. Think about what we're actually doing here. We're solving the equation sine B equals 0.5107. So on the unit circle, your good old unit circle from however long ago, this is asking where is the y value equal to 0.5107. So here's 0.5107 on the y-axis. So how many angles should we get where the y value is equal to 0.51? You should get two, right? You should get one angle in the first quadrant, and you should get one angle in the second quadrant. So this could be B, or this could be B, or they could both be B. They could both be valid solutions. This is why side-side angle is called the ambiguous case, because you could get two possible angles that satisfy law of sines. The first one in the first quadrant is going to come from doing sine inverse. So when you hit sine inverse on this, what do you get? $30.7105 degrees. So that's this guy. How would we get this bigger angle in the second quadrant? Since we're in degrees, instead of using pi, what would we use? 180. Did I get that right?
Yeah.
Now, here's my question. Do I care about this angle? Why not? It's too big. Why? Because you already got 50 in there. If I didn't have 50 in there, if I had like 10 degrees in there, this would be fine. 149 would fit. But you can't fit 149 up here if you already have 50 down here. So this solution, even though it solves this equation, is not valid in our particular application. So A equals 50 and B equals 149 point whatever can't work. Can't form a triangle. So this solution I'm going to ignore. This won't always be the case. Sometimes you will have to include this solution, and that's when you have two possible triangles coming out of your law signs. But for this particular example, only 30.7105 will work. How do you think? So I've kind of given you a clue as to how you can get two different triangles, because you'll get two different solutions for B here. How do you think I could get 0 triangles out of this? They won't both be too big ever, because this is always in the first quadrant. But what can happen is you can get no solution to this. How would you get no solution to this equation? If you had bigger than 1 on this side. Right, so if you had sine of B equals 1.5, it's not possible. So you won't be able to form a triangle. The sine is always between -1 and 1. So look out for this first equation here. Tells you how many triangles you have. This, along with the fact that we started with 50 degrees, allows us to rule out the second solution. Okay. Cool. Great. Fantastic. So once we have B equals, can't form a triangle. So once we have B equals 30.7105, how do we get the remaining pieces of information?
You figure out what C is.
And how do you get C?
180 minus.
You can subtract now, right? So to solve for C, solve for big C, the angle C, you would take 180 minus 50 minus 30.7105. So now I have this guy, found him. So the only thing left is little c, the last man standing. How do I get him?
Little C over.
Well, signs again, yeah. I would probably compare, don't use B again if you don't have to, since he has rounding error in him. So go ahead and use big A and little a against big C and little c. So to solve for little c, I would set up little a over sine big A equals little c over sine big C. And I know these 30 over sine 50 equals little c, which I don't know, over sine 99. Cross multiply, 30 sine 99.2895 should equal c times sine 50. Then divide by sine 50, and you got your c. What do we think?
38.6486.
38.6486? So final answer, I needed to solve for big B, big C, and little c. Because the instructions say round to the nearest degree on the angles, at the end of my work I'm going to round this up to 31. Big C is going to get rounded down to 99, and little c is going to get rounded to the nearest tenth, which is 38.6. It's not hard, I don't think. The only tricky part about this, the only thing I've found that students have a hard time with, is figuring out how many triangles you have. Right here, where we have to eliminate this solution. Most of the time, the reason they have a problem with it is because they don't even remember to get this solution in the first place. But if there's two triangles, if there's two possible triangles, we need this solution to get our second half of the answer. So that's the next one. We have two triangles to deal with. Let's look at that bad boy. Part C gives you little b equal to 12, little c equal to 16.1, and big B equals 20 degrees. So I draw my schematic. A, B, C. A, B, C. And I know 20 degrees for big B, and then 12. 16.1. So you'll notice I'm in the annoying case, the ambiguous case, where I have side, side, angle. So I have two sides and the excluded angle. Which means I could have 0, 1, or 2 triangles depending on how the numbers work out. So, I set it up. A over sine A equals B over sine B, C over sine C. I know little c, and I know big B, and I know little b. So I can solve for big C right away. Solve for this guy immediately. Using the lawofsines. So I'm going to set up this argument here, little b over sine big B, 12 over sine 20, equals little c over sine big C, 16.1 over sine c. Do your cross multiplication to bring up the denominators. 12 sine c equals 16.1 sine 20. Divide. Sine c equals 16.1 sine 20 over 12. Four, 5, 8, 9. Checking. So then, how do I get C? Yeah, you gotta be careful, right? How many answers am I expecting for C here? 2, right? You have one in the first quadrant, one in the second quadrant, always. The y value equal to 0.45 is right here. 0.4589. So you can either be here or here. So this could be C, or this could be C. So what do you get when you hit sine inverse? 27.3161. Which means when you also have to subtract that from 180 to get your other possibility. Save me the work. 152.6839. Good. Now, do both of these work in our original triangle? Yeah, the only measurement we have so far is 20 degrees. Right? And if you add 152 to 20, you're under 180. Right? 152 plus 20 is going to leave us at 172, which is under 180. So both of these are okay. So what we have then is a C1 equal to our first angle, and a C2 equal to our second angle. So we have this, we have two choices for this guy, which means we're going to have two choices for both of these guys. So we're going to have to find, associated with C1, we have to find a little a1 and a big A1, and associated with C2, we have to find a little a2 and a big A2. So let's focus on big A1 first. How can you get the angle big A1?
180 minus 16.
180 minus what you already know. You know B, you know C1. So big A1 will equal 180 minus 20 minus big C1, 27.316. 142.6839?
No,
130. Okay. So this is one of the angles we're going to use for our solution. While we're at it, we might as well get big A2, since that's pretty easy. What changes when you solve for the second angle, big A2?
You start, C2.
Big C2, right? So we'll do A2 equals 180 minus 20 minus 152.6839. 7.68 or 7.316. 7.316. Big A2 is done. Oh, tedious. This is why I wasn't in there. So then I know this. Right? I've changed this to a known. Which means the only thing I'm missing is my little a1, my little a2. So I solved that. For little a1, I'm going to use, let's see. I know big A1. Should I use B and sine B, or should I use C and sine C?
small b.
Yeah, you want to use B and sine B because those are the given information. So to solve for big A1, I'm going to set up A over sine big A, but I'm going to use big A1. That'll give me little a1. Equals, then I do B over sine B. So sine, on the bottom, I'll sine 132.6839 equals 12 over sine 20. Cross multiply, A1 sine 20 equals 12 sine 132.6839. Divide by sine 20.
Josh, where did you get the 152? Oh, it's A1. Okay,
A1, you have to use A1.
got it.
So then little a1
25.7916.
means, and although you wish you were done, you are not. Still have to get little a2. I'll write something you can tell me if you believe me. Little a2 should be equal to 12 sine 7.3161 divided by sine 20. What do you think? You agree? Right, the only thing that changes for A2, you set up the same exact thing, except instead of using the angle A1, use the angle big A2. So instead of 132, you'll use 7 degrees. Which means this will be 7 degrees, which means this will be 7 degrees. Which means you have to do this. But you can set it up and do it. I have faith that you will get this.
4.4671.
4.4671.
9.
9. 4.4679. All right. So what are my answers? Let me see if I can make any sort of sense out of this. So triangle 1. I have big C1, which I'm going to round to the nearest degree, now that I'm doing my final answer. Big C1 will be 27 degrees. Then I went on to get big A1, which is 133 degrees. And then I went on to get little a1, which, since it's a side length, I'm going to round it to the nearest 10, because that's what the instructions say. So little a1 will be 25.8. So this is for my first one. For my second triangle, I need to do C2, A2, and little a2. Round those guys off. C2 is 153. A2 is 7. And little a2 is 4.5. So, what does this mean? Does this mean anything?
Two triangles.
So, if you start with an angle of 20 degrees, like this, 20 degrees, for your B, and you have an opposite side length of 12, with C being 16.1, right? One of the possibilities is that A will be 133. So one of the possibilities is that you will have a large angle here of 133, keeping this guy 12. And then you'll have an A1 of 25.8. So this will come down and meet with this at 25.8 units. And then C1 will be 27 degrees. So this is the first triangle you can get out. In the second triangle, A2 is a lot shorter, so basically what's going to happen, D is still going to have to be 20 degrees, that doesn't change. So I'm still going to have a 20 degree angle here. C is still going to be 16.1. But now big C2 is the bigger angle and A2 is the small angle. So see how this angle was 133? Now it's going to end up being 7, like this. So this will still be 12, but now the opposite side length will be 4.5. Right? It's not nearly as big on the opposite side of A anymore. And then the one I didn't label, 153. Right here. So each of these have the same starting conditions. But you get two distinctly different triangles. So that's what sucks about side angle. And undoubtedly on a quiz you will definitely end up with two different triangles. So if you didn't understand, how do you tell? How do you know? What's the key that you have to look for here? The first time you solve a sine equation, like we had this, the first time you solve this sine equation, you always want to write down both your solutions. Right? C equals theta, C equals some degree, right? In this case it was 27. and also C equals 180 minus that. So this is where the difference is. All right, so I'll stop here. I'll do log cosines on Monday.